really expensive compared to the metal alloys per kilogram. So we've got to find some justification for it. And the two reasons that are usually quoted are its doinginess and its strength. Now this is a graph of specific stiffness and strength, and the specific part of it just takes into account its density. So if you have something with a high specific stiffness, it means that you can have a high stiffness, but with lower weight. And we can see that carbon fiber sits right at the top of the scale. It's really high specific stiffness and really high specific strength. There's also another point here, which is carbon fiber composite, and that sits a little bit further down. And the reason why this sits further down is because composites are made out of two parts. The first part is the fiber, which is the super strong and super stiff stuff. And then the second part is the matrix, which essentially it binds the fibers together. The problem is the matrix is usually a very low stiffness and a low strength. So hence the resulting composite properties that you get is an average of the two, which is why it's further down the graph. And so how strong is strong? If we focus on the composite side of things, the carbon fiber composite, we quote strengths of about 3,000 megapascals. Now, what does that actually mean? Well, did a little bit of calculation here, and I like to put things into perspective in terms of micros, because I weighed my micro once, and it was 900 kilos. So if we wanted to break one of these carbon fiber rods, which is 4 mil diameter, we would need 4 Nissan micros suspended at the end of it to break it. And this is in comparison to 1 micro for steel, if it was the same dimension. And yeah, so it's pretty strong stuff. Also equates to 1 elephant for carbon fiber. However, this is only in the fiber direction. If we turn the fibers at 90 degrees, so that in this rod the fibers were now running this way, it would only take 1 person to break it. So there's a big disparity in the strength of the material depending on the fiber orientations. And this is absolutely central to how we design with composites. So what I want to talk a little bit more about is how we actually do composite design. Because of these different varying stiffnesses, we can actually tailor the properties of the laminate to our loading conditions. And there are 2 loading conditions I'm going to talk about. The first one is bending, which is when you do that to a material. And this essentially is applying a tension load on the top and a compression load at the bottom, right? So if you wanted to stiffen it in this direction, you'd actually have to run fibers in line with the bending. And you can see this with corrugated card, which is a really great prop. If we see the corrugations represent fibers here, you can see that it bends really easily perpendicular to the fibers. However, if you turn it around and bend it with the corrugation, it's actually pretty stiff. So if we wanted to stiffen it in both directions, in this way and in this way, what we do in a composite is we lay up 1 at 0 degrees, 1 at 90 degrees, and essentially we have a composite that is stiff and bending in both axes. The other thing I want to talk about is torsion, or shear loading. And for this, my next prop is 2 bits of card with a bit of string in the middle. And this floppiness of the string will show us where the load path actually goes when I apply torsion to this, which is I keep this hand still and I twist with this hand. And you can see that the fibers actually rotate. Now, if I can open this up, yay, almost. Essentially what we're doing is we're applying a shear in this direction. And you can see that the fiber directions that need to be here to resist that is going to be at 45 degrees. So hence, we usually put plus minus 45 degrees in our laminates to resist this torsion in tubes. Plus minus because we want to resist torsion one way and also the other way. So with these 2 loading conditions, we can specify what stacking sequence, what fiber orientations are in the laminate. And depending on the beauty of composites, it's depending on what loading conditions we have. If we've got lots and lots of bending, we can put lots and lots of unidirectional fibers in, which is fibers in line with the bending. If we have a little bit of torsion, we'll put a little bit of plus minus 45, and so on and so forth. And this actually leads us on to what's really great about composites. And I want to introduce to you a very, very special bike. Super awesome, ultra cool. This is the Lotus Sport mountain bike. It was designed by Chris Hornsey Jones, who's actually a local guy here. He's my boss, and unfortunately he couldn't be here today, but his bike is. And yeah, it's a really beautiful bike. This exemplifies what we can achieve with composite design. We've got complete freedom of the form here, so the geometry is just beautifully organic. Yet the bike itself exhibits these desirable qualities of stiffness and strength and vibration damping, all because we can tune the fiber orientations and also the fiber types. So what's really, for me, one of the really interesting things about this bike is the rear end. It's actually got rear suspension, although you don't see any forks here. And the rear suspension it happens in this part of the bike, which is the chainstays, and it happens with composite flex. Now we've got a few different requirements at this end of the bike. We want it to be relatively compliant in the vertical direction to give us ride comfort, so we don't spring out of the saddle every time we hit something. But we also want stiffness in the lateral direction, so lateral bending, we want it to be stiff, and also torsion in this tube for pedaling efficiency. Otherwise, we're very inefficient and we go around boing, just like we're walking. And we can achieve this through tuning the laminate layout so specifically to this. And this makes a really, really nice ride. It's such a great bike to ride. It's just amazing what they managed to do with it. And next thing is, just because we're running out of time, I want to fly through this. Potential future in composite and bike making. This stuff is actually in the automotive industry and also in the aerospace industry. It's about weaving and braiding composite fibers. So essentially what you could possibly have is like the whole bike frame itself braided as a preform, which you then just infuse resin through it. That could be really cool because it might reduce the cost, it might give you a better efficient usage of the material, which means that you might get a lighter bike as well. And second thing is, this is really, really exciting. This is going to be released really soon, or it has just been released. It's 3D printing, but it uses carbon fiber. I mean, imagine that, it's desktop size as well, so you literally have a 3D printer in fiber here, and your desktop here. So you can design your own components and actually print them off. And this is the great thing about it, is that it just makes it accessible to everybody, rather than being some sort of big manufacturing technology that we kind of know nothing about. It makes it a lot more approachable. So just like to leave you with that thought, carbon fiber.
So from the future, straight back to the past. This was a bike designed in the 1890s, and it was because some guy realized that if you didn't ride so tall in the saddle, if you lay back a little bit, riding would be easier. Nobody took much notice till 1933, a guy called Charlie